Hello again. Lou McIntyre here with some more insights into the special theory. Let's get into it. In this video, we will talk about the Michelson Morley experiment that led to the Lorentz transform and the theory of special relativity. We will show you exactly how that experiment led to the Lorentz transform and how that transform works in a very clear way. We will show you the role Doppler shift plays in transforming a measurement from one reference frame to another. First, we need to look at the theories of light in the 19th century. Isaac Newton came up with the corpuscular theory of light that it was made up of tiny particles. This remained in vogue until the early 19th century when Thomas Young's double slit experiment verified Christian Huygens' wave theory of light from a century before, which then became the dominant theory. Waves need a medium in which to propagate, and so the hypothetical luminiferous, or light-bearing, ether was proposed. In the mid-19th century, James Clerk Maxwell defined the set of electromagnetic equations. An electrical field flows from a charged source or a sink. A magnetic field has no sources or sinks. Electric fields are generated by time-varying magnetic fields, and magnetic fields are generated by electric current. He determined that light is electromagnetic radiation, with a theoretical speed of propagation related, interestingly, to the resonant frequency of space. So the search for the luminiferous ether was considered the final problem to be solved in physics. Little did they know that the search for this non-existent entity would soon explode in the 20th century with special and general relativity and quantum mechanics. Albert Michelson graduated from the U.S. Naval Academy almost 100 years before I did, in 1873. I took modern physics in Michelson Hall, named after him, my last year there in 1970. After one sea tour, he returned to the Academy in 1876 to teach physics. In 1879, he measured the speed of light as a class project for his midshipmen, using a rotating mirror, coming up with a speed within 0.1% of the modern accepted value. He left the Navy for the Case School of Applied Science in Ohio, where he collaborated with Edward Morley to conduct the Michelson-Morley experiment in 1887, for which he became the first American to be awarded the Nobel Prize in Physics. So what was the Michelson-Morley experiment? Maxwell's equation for the speed of light did not incorporate relative velocity. It was assumed that light speed was defined in the ether, which was assumed stationary in space. Michelson and Morley proposed an experiment using the Earth's orbital velocity around the sun, 67,000 miles per hour, or about 1/10,000th of the speed of light. They used a light source through a half-silvered mirror, splitting the light into a north-south and an east-west beam, recombining them to an interferometer. As the platform was manually rotated, there should be a change in the interference fringes, since the north-south crosswind path should have a higher net velocity than the east-west upwind-downwind path. This was the first setup, a heavy stone slab carrying the experimental rig floating in a pool of liquid mercury that allowed its easy rotation. This was later repeated in a larger setup in the basement of a building with longer paths with the same result. The speed of light was unaffected by the velocity of the Earth around the sun through the stationary ether. This was perhaps the most famous null result in history. Various theories were concocted to account for this null result. The Fitzgerald contraction had the greatest legacy. If the slower east-west path were somehow shortened in the direction of motion, this could null out the change in velocity. Oliver Heaviside noted that the electrical fields were contracted in the direction of motion, and George Fitzgerald extended this to all matter without any theoretical basis. This fundamental belief that relative velocity affects the space and time of the moving body ignores the fact that from the point of view of the moving body, it's at rest and the observer is moving, and therefore it is the observer's space and time that is affected. Also, there is no absolute velocity. Besides the Earth around the Sun, the fastest known speed in 1887, the Sun moves around the Milky Way 6 times faster. And our speed with respect to the farthest galaxies is near to the speed of light itself. Which relative velocity affects our space and time, which we cannot detect? Now we come to the Lorentz transform. Hendrik Lorentz derived the transform bearing his name. The Lorentz transform is actually the basis for the theory of special relativity. He derived it from the familiar Galilean transform, which simply relates measurements between 2 reference frames in relative motion. He applied unknown weights alpha, beta, and gamma to the Galilean transform so that both reference frames will measure the same speed of light. Solving for these unknown weights yields, after some messy algebra, the Lorentz transform. The transform is simple enough, but to date, no one has come up with a good graphical solution for it, or even, in my opinion, a good explanation. It's generally explained that space and time is contracted and time is dilated by relative velocity through some undefined process. However, both reference frames view the other space and time being contracted or dilated as shown by its bidirectional forms, with the transform from S0 reference frame to S1 on the left and S1 to S0 on the right. I'm going to therefore offer my own explanation. I use the trigonometric form of the Lorentz transform with the Brem velocity angle beta equal to the arcsine of V over C. This gives an excellent geometric view of the Lorentz transform. The Lorentz transform uses the weighted Galilean transform. What does this weighted Galilean transform look like? It's surprisingly simple, just x0 foreshortened by the cosine of beta. Let's prove it. x1 at time equals 0 is calculated by setting ct1 equal to 0 to determine ct0 in terms of x0, and then using that value to determine x1 when ct1 equals 0. Next, we determine x1 for all time by taking the Lorentz transform of ct1 in the weighted Galilean transform to find that this yields, after removing the trig identity, the Lorentz transform for x1. Thus, the weighted Galilean transform locates all the measured points of ct1 and x1 that are the Lorentz transform of ct0 and x0. Let's see how this works. We begin by locating the measurement A in S0 at time 5 with x equal to 2, marking it with a circular symbol to indicate that it is a measurement. S0 cannot transmit this measurement until A prime, when light from A reaches the observer on the origin. This equals the sum of CT0 and X0, 7 units of time. S0 communicates its measurement to S1 by light. Doppler shifted with equal units of space in S0 and equal units of time in S1 to locate B prime, which is S1's time of receipt. This occurs at CT1 equal to 12.12 units of time. The Doppler shifted sum of CT0 and X0 can be rearranged to show that it is equal to the sum of the Lorentz transform for CT1 and X1. This indicates that it is simultaneous with light from the Lorentz transform of CT0 and X0. But where is that measurement? That measurement is on the weighted Galilean transform at C prime. The Galilean transform is shown as a blue dash. Which is the locus of measurements in S1 of the Lorentz transform of CT0 over time, in this case, C prime at CT1 equal to 6.92 units of time and X1 equal to 5.19. These two numbers also summed 12.12 units of time. We can show graphically that it is the Lorentz transform of S0 by erecting a temporary X1 axis at CT1 equal to CT0. Proceeding from A prime in the direction of CT0, then an equal distance in the direction of CT1 to locate C prime. Both reference frames determine the same speed of light from measurement to observation. Interestingly, each reference frame observes itself stationary with respect to light and the other one moving. The measurement from C prime, a fixed point on S1's ruler, is simultaneous with Doppler shifted light from A prime. And the measurement is located on the weighted Galilean transform. This satisfies the simultaneous set of equations that Hendrik Lorentz set up to create the transform bearing his name. This was set up to explain the Michelson Morley experiment's failure, which in fact can have no other result. If A were one of the two mirrors in that experiment in the upwind, downwind direction, and the other were in same distance in the y direction in the crosswind path coming perpendicular out of the plane of the page, you will see that both mirrors are at rest in S0 and relative motion with respect to the sun or any other body will affect them not one whit. It will be the observer on the CT1 axis that will determine that the mirror in the x direction of motion was shortened by the cosine of beta, while the mirror in the y direction normal to the relative motion was unaffected. So in summary, The Lorentz transform is simply a Galilean transform weighted to ensure that both reference frames measure the same speed of light. Although it was derived to explain the ad hoc Fitzgerald contraction in the obsolete ether theory, its basic assumptions are valid and were incorporated into Einstein's special theory of relativity. And that theory extended them to cover mass, energy, and momentum. If you are confused by what you see others explaining special relativity, it is the widespread belief that the event and the measurement are the same point, measured differently by two reference frames. And any differences between the two measurements has to be due to effects on the event's clocks and rulers, since obviously our measurement is perfect. But as we have seen, they are not the same point. Before we can locate an event in time and space, we must receive light from the event, Doppler shifted by its relative velocity to us. This affects the time at which we observe the event and subsequently the location that we determine for it. It is our measurement that is affected by the event's relative velocity to us and not the event's clocks and rulers. I hope you will find this explanation a little more clear than others you may have seen, and I hope you enjoyed this presentation. Perhaps you learned some things you didn't know about the Michelson Morley experiment and the Lorentz transform. If you want to learn more, read my book, Writing on a Light Beam. You can purchase it on Amazon or via my website shown. And don't forget to press the like button. It helps to make this YouTube presentation more widely available. Thanks again for watching.